Hey everyone, and welcome back to the channel. Today we've got another problem breakdown for you. We're going to be doing design WhatsApp or design Messenger. This is a really common question and one that people are constantly asking us for a YouTube video. So here I am before the end of the year giving you that YouTube video. For you, those of you who are new to the channel, we are Hello Interview. We're here to help you prepare for your software engineering interviews. This channel is loaded with guides, deep dives, and problem breakdowns that will hopefully help you prepare for system design. We also have a ton of content on the site talking about behavioral interviews. We've got animated coding solutions and patterns, lots of stuff that we think will be very helpful for you. For me, I'm Stefan. I am one of the co-founders of Hello Interview. I have also worked as a senior manager at Meta and then at Amazon, where I conducted north of 2,000 interviews. So I am very familiar with the process and hoping to share some insights as we walk through. But I don't want to spend too much time. If you like content like this, please like the video, subscribe, and let's go ahead and dive in. Before we dive in, I wanted to introduce our delivery framework. This is just basically a series of steps that you'll follow in order to conduct your system design interview. Now, for mid-level and senior candidates, I highly recommend that you follow this as closely as you can. If you're a staff level candidate, you've got 20 years of experience, and you want to go outside the line, great. But the purpose of the delivery framework is to make sure that you cover the important bits of the design and also to help you to think about the problem as you work through it. What we find is that candidates who follow this framework tend to, on average, and there's certainly exceptions, perform better in interviews than candidates who don't. Now, I'm going to actually try to follow this as closely as possible for this video so you can get an idea of what that looks like. And then I'll earmark those places where I'm diverging or giving you some additional detail that may not actually be part of your interview. But the first step is requirements, and that's where we're going next. This is a place where we can have a conversation with our interviewer to really understand the scope of the question. And sometimes we can even debate what's in and out of scope. In the ideal case, once we've set our functional requirements, we can actually use those as stepping stones for our high-level design. And for a lot of candidates who get lost or have difficulty managing their time, it usually comes back to them not setting good and actionable requirements. So do spend time here. We generally recommend candidates spend about 5 minutes. And what that gives you enough time to do is to think through all of the different product edge cases to come up with a concise set of functionalities that you need, as well as the non-functional or constraints on your system. So for WhatsApp, the easiest way for me to come up with functional requirements is to put myself in the shoes of the end user. So I open up the WhatsApp app. What do I see? Well, the first thing that I see is a list of all the chats that I have with other people or other groups. But in order for those chats to exist, I have to have created them. So let's go ahead and assume that one of my functional requirements is to start group chats. I'm going to use group here as like a general case. If I've got a group of 2, that's a one-to-one message. Now, once I've got those chats in place, the next natural requirement is for me to send and receive messages between different users. My expectation is that if I send a message, it goes to all of the members of that chat. And if anybody sends a message to a chat that I'm a member of, I'm going to receive that. Now, it's a natural question here to ask, are there constraints on these messages? Do we want to support video, audio? And maybe my interviewer says, yeah, we should definitely do that. So we add media attachments to what we're going to design. Another thing that we should probably think through as the candidate is what happens when our clients go offline. If you're designing a product that has a mobile app, those mobile apps are going to disconnect periodically. Maybe I turn off my phone before I go to bed. And in that case, for WhatsApp, I would expect that when I wake up and turn my phone on, that I'm actually going to get all the messages that I received when I was offline. So I'd like to be able to access the messages after I've been offline. I can go into additional detail here. I can ask my interviewer about whether we should support video and audio calling, whether I need to be able to see whether my friends are online or offline. But generally speaking, we should try to keep our requirements pretty short. And there's no actual need for me to go ahead and say, I need below the line audio video calling if I don't have time. Now in this case, I've spent about 2 minutes getting the base functional requirements. I have some additional time here where I can discuss with my interviewer some additional functionality they might be planning, but be careful about expanding the scope to be too extensive. If you do, you're going to create problems for yourself. If you're low on time and you didn't just rattle off those requirements, I've obviously thought about this problem before, then don't bother wasting your time trying to enumerate things that you're not going to include. It's a good idea to ask your interviewer, hey, do you have anything else that's in mind? And then move on. Next, I'm going to move over to my non-functional requirements. And here I'm going to try to describe how the system performs. These aren't end-user functionalities. These are things that my system ought to do while I'm making those functional requirements real. So the first thing that most people are going to think of when they think of a chat app is low latency. I'd like to be able to get my messages in a short amount of time. Now, a lot of candidates will stop here and they'll say, oh, it should be low latency. But I would actually encourage you to quantify these non-functional requirements where possible. In this case, let's think, what would be an appropriate latency for a chat application? Well, it turns out that most people aren't going to have two phones sitting in front of them looking to see if I send it from this one, how quickly do I receive it? So we've got to figure out what would be perceivable. Well, if you were sitting across from me and I sent a message and I had to wait a few beats before I got a message, that would seem slow. But the difference between 100 milliseconds and 500 milliseconds is not really all that noticeable. So we want to give ourselves a bit of room here in our design, and we don't need to unnecessarily make this low latency. So let's go ahead and assume that it's 500 milliseconds of latency. This is going to come back later on in our design because we'll be able to use that 500 milliseconds and ask whether we have budget to do different things. The next thing that we might think through is that we want to make sure these messages actually get to their recipient. It would be weird if I sent a message and they were like, well, I never actually got that. So we'd like to be able to guarantee that the delivery of messages actually happens. The next thing that we're going to think through is, what's the scale of this system? And oftentimes candidates will try to make assumptions here about the size of the system. For most of the web scale systems, it's usually a decent assumption to assume 100 million or a billion users. And in WhatsApp's case, I think it's actually a couple billion users. So let's just go ahead and say billions of users. So we need high throughput for our system. We're going to have to handle lots of messages. I'm going to defer here in trying to come up with the actual number of messages that the system needs to receive and send, because I'll be able to make more informed estimates of that later on when I know more about my system. I don't need to jump into back of the envelope calculations just yet. The next thing is specific to WhatsApp. I don't want to store messages unnecessarily. So ideally, I'd like to keep the messages on the server just long enough to be able to perform my functional requirements, and then I'd like to get rid of them. If you think about privacy, and WhatsApp is a very private app, then data is like toxic sludge. It's something that you don't want to keep around, that ideally you're either actually deleting it or you're encrypting it in a way that even you can't access it. So that way you don't have the liability on your hands. The last thing that an app like WhatsApp probably needs is to be able to tolerate faults. This is a gigantic system. We're going to have things that are failing all the time. Ideally, these individual components aren't going to take down our app. This is generally true of most apps, but it's especially true of WhatsApp, and so we're going to include this in our non-functional requirements. Now, we might talk about additional things here, like should we be able to prevent spam and security issues? Should we have to deal with scraping or people trying to get contact information from all WhatsApp users? I'm not going to go into those, but if I had additional time, I'd mark those below the line and move on. Now that we've got our functional requirements, our next stop in the delivery framework is our core entities. Core entities are not an explicitly evaluated part of the interview. You're not going to have interviewers who are writing in their notes, hey, they got the core entities wrong. Generally speaking, what they're evaluating is that final design and kind of the process through which you came up with it. But core entities are really important in that it's easy to make mistakes in your design if you don't get the entities right. This is also a place where you can have some discussion with the interviewer about the identities of various items. Especially in product style interviews, being able to think deeply about the identities of entities in your system is going to make a world of difference in your data model, in your API, and so forth. And so for some interviews, like Meta's product architecture interview, being able to reason about these entities is really important. Now for this problem, we first want to talk about the actors of our system, who is involved. And in this case, all users are kind of on equal footing. We have anybody can send messages between peers on our network. We don't really have any privileged actors. If we were designing Uber, we have riders and drivers. If we were designing YouTube, we have creators and viewers. But for WhatsApp, all users are peers. And so we can leave it at that. Once I've got the actors, I can work through my functional requirements and make sure that I've got nouns that reflect all of the things that I need to do. So the first thing that I need to do is set up a chat, and inside my chat, I can send and receive messages. Now, when I want to access messages after I've been offline, I think it's important to recognize that a person isn't offline, a device is offline. I turned off my phone and now it's back on, but my laptop's been on the entire time. And so I need an entity to reflect my clients or maybe my devices, so that way I can keep track of where have messages been delivered. I want to know that all of the messages have been delivered to my phone and my laptop eventually. I've got a pretty good set of entities here that cover my functional requirements, so I'm going to keep moving. I'm not going to spend additional time here, but I've given some good discussion that tells my interviewer I'm thinking deeply about the nouns and the entities in my problem. Our next step in the delivery framework is for us to talk about our API or system interface. And before we go there, we need to first think about how we actually make connections between our app and the backend servers. On our website on Hello Interview, we have some premium content. One of those deep dives as part of the premium content is our real-time updates deep dive, where we talk a lot about connectivity and the various options for making connections between clients and servers. And you've got a lot of options here. You can use long polling, SSE, we can use WebSockets or WebRTC. One of the ways that we talk about how you can kind of reason through whether you're going to need to use one of these technologies is based on whether you are very latency sensitive. If not, you should definitely use polling. In this case, we need to deliver all our messages in 500 milliseconds, so that doesn't apply. The next thing is whether there is frequent bidirectional communication between the client and the server. In this case, yeah, messages can be coming back and forth for our chat app quite frequently. So we can't use SSE in this case because we also need to be able to send messages quite rapidly. The last consideration for us is whether we have peer-to-peer or need audio and video support. We don't actually need that for WhatsApp with the requirements that we're given. So the natural conclusion for us here is to use WebSockets. I think in WhatsApp, the real app, they're just using a simple TLS connection. They're not using the overhead of WebSockets. But the same principle applies here. We need a persistent connection between the client and the server that we can ferry messages back and forth. So a RESTful API for WhatsApp probably doesn't make as much sense because it doesn't give us a way for us to send those messages back from server to client. So now that we know that we're going to be using WebSockets for the connection between client and server, we can talk about what our API looks like. And this isn't going to be a traditional RESTful API. There really is no standard for describing a WebSocket API, but I think an easy way to talk about this is commands that are being sent from the client to the server, as well as commands that are going to be received by the client from the server. In terms of commands that are going to be sent, well, we can go back to our functional requirements to reason through this. First of all, we need a way to create a chat We also need a way to send a message. We may need a way to create an attachment. We'll think about this as we go into our actual design, how this might work. And then we might need a way to modify the participants that are existing in a chat, maybe to add a user or remove a user. We could clearly think of lots of other functionalities, but we're going to stop here to make sure that we cover our functional requirements. In terms of commands that are going to be received, well, we need to get a notification to our client whenever there's a new message. We need to be able to send and receive messages. We also need to get updates when new chats are created that I'm added to, or maybe when participants change. So that way I'll know that, Sandra is no longer part of the group chat. Maybe she's on the outs with our social group. Now, I can obviously go into detail about the body and contents of each of these, but I'm not going to do that here, in part because the rest of the design is going to take a lot of time. So what I'm going to do is I'm going to tell my interviewer, hey, I think this is the rough scaffolding, but I'm going to come back to this as I get more clarity on the details. It's very common in system design interviews to be somewhat iterative, and especially for the API and high-level design, there usually is a bit of a back and forth. And most interviewers understand that this is what's going on. So my recommendation is that you tell them, hey, this is just the start, and I'm going to come back to this as we have time. You may not have time, but at least they recognize that that this is not a complete description. The trick is you don't want to leave your interviewer in a lurch. So what you don't want to do is make an obvious mistake or do something that looks incorrect and then make it seem as though you don't know that you've made a mistake. What happens then is your interviewer stews on that. They might make a note in their interview notes, and the base assumption is that you missed that, even if you had it in the back of your head. So communicating proactively about where you're going to stop short or where you're making an obvious mistake is really important to making sure that you land that interview. Now that we've got our API, we can move on to the next step. We don't actually have a data flow requirement here. This isn't a particularly data-heavy infra system, so we can move straight into everyone's favorite, the high-level design. I've actually moved the functional requirements up here so that we can refer to them. For the high-level design, our recommendation is that you actually work through your functional requirements and try to satisfy them as simply as possible. Now, it can be tempting to try to jump ahead and build a highly optimized, scalable system out of the gate. We don't recommend that you do that. For certain candidates who are very experienced, go ahead, skip a step. If you've got a staff level interview and you don't want to go through all of the basics, I think that's completely acceptable. But for most candidates, it can actually be useful for you to build the basic system and then progressively and organically evolve. Why? Well, two reasons. One, this is how systems are actually designed in the real world. People aren't just jumping to optimal system, they're organically evolving them over time. And secondly, it's very easy if you try to jump to optimality to both leave gaps and holes, but also to have instances where you kind of lose track of where you are and what you needed to do. If I'm getting lost in some scaling consideration, I may not build out all of my functional requirements, and the system isn't working. It's hard for my interviewer to give me credit in those instances. So get really good at banging out a system that satisfies the base functional requirements, and then layer on some of the scalability and non-functional aspects of the system. So with that in mind, let's go ahead and start with our first functional requirement to be able to start group chats. For this, I'm obviously going to need a client, and that client is going to make a connection to a chat server. I'm going to assume that this is a single node chat server. I just have one instance, and that's going to simplify things dramatically and then create problems that I'm going to go ahead and solve later. That chat server needs to communicate with a database. I will go ahead and use DynamoDB here, but we could realistically use any key value store. We could also use a relational database. I think a lot of people get hung up on relational databases thinking they don't scale. think Shopify just released some of their numbers for Black Friday, saying their MySQL instance was doing some number of millions of transactions per second. The idea that relational databases somehow can't satisfy these high scale situations is just simply not true. Although some interviewers might mistakenly perceive that to be the case, in which case, go ahead and try to adapt for, in some cases, their ignorance or out of date ideas about what's possible. In this case, we'll go ahead and use DynamoDB. So our clients are going to make WebSocket connections to our chat server, and our chat server is going to connect to our database. Then our client can send that create chat message to the chat server, and then the chat server can create a record in our database. Well, what tables do we need in our database? Well, first of all, we need a chat table. That's going to be really important for us to be able to store metadata about the chat. Maybe we have the ID, the name of the chat, potentially some additional metadata that we might need. And then we also want to know who is in the chat. So we'll include a chat participant table, and that will have a foreign key or a reference to the chat ID, as well as a participant ID. Now, the interesting thing about this is that when we create a chat, we typically want to do two things. One is we want to be able to find all of the participants in a given chat. And then the next thing is we want to be able to find all the chats in which we are participant. So for the first style of query, we can go ahead and use a composite primary key on this chat ID that basically allows us to look up all of the participants given a chat ID. We can use the participant ID as a sort key. For the latter query, where we want to find all of the chats that I'm a participant on, we can use a global secondary index, or GSI. And basically, this is a functionality in Dynamo that allows us to create an index which enables these rapid lookups without having to organize our data in a specific way. And so with that global secondary index, we'll be able to query all of the chats that I'm a participant of. And that gives me a basic system that allows me to start group chats. Now that we've got our chat set up, we can start to think about how to send and receive messages. This is a little bit easier in this degenerate case where we have a single chat server. I'll tell you why. All of our clients are connecting to the chat server via WebSockets. So we might have 1,000 connections for clients to the chat server. When we want to send a message, the client will send a send message request to the chat server with the chat ID that it wants to send it to. The chat server will then query the chat participant table to go and find all of the participant IDs that it needs to send that message on to. Now we need to go and send those messages back to the client. How can we do that? Well, the nice thing is this chat server maintains connection for all of the clients that are currently connected. So what we would do is we would have a simple hash table, and it would say client A is connected to WebSocket 1 and client B is connected to WebSocket 2. And now, once we have all of the participant IDs, we look up the client ID in that hash map, and then we find the associated WebSocket connection, and we send that new message command back to the client so that they can receive it. So in this case, we don't have durability. The messages aren't stored anywhere. We can only send and receive messages to people that are currently connected to the chat server. But being able to have kind of a live chat room is fairly straightforward, and the messages get sent. We look up the participants. Based on the participants, we find the associated WebSocket connections, and we send them back to the client. Now that I can send and receive messages, let's talk about how I can send and receive media. The idea here is pretty simple. I have a baby picture or a video of my kids, and I want to send it to grandma and the rest of the family. How can I do that? Well, the most naive thing that we could probably do here is we could create an attachments table in DynamoDB. And then what we could do is when users want to send those videos, they could send a message in that existing WebSocket channel to our chat server, which can then write that data to our attachments table in DynamoDB. Then when we need to receive those messages, we would load all that data and send it back to the client. This is broken for two reasons. The first reason is that Dynamo really isn't intended for large blob storage, especially if you're talking about videos, which could be hundreds of megabytes. This is really not a good use case for DynamoDB. And the second thing is we're using our already exhausted chat servers for this very intensive high bandwidth use case of uploading media. If you can imagine, we've got this disparity between these gigabyte payloads that are happening when I upload the video of my kids for grandma, and then the OMW messages that I'm sending to other users to let them know I'm on my way to the movie theater. And that disparity is usually a sign that something is wrong. So a lot of candidates will rightfully reach to a blob storage here. Since we're already using AWS, why don't we go ahead and use S3? Instead of having this attachments data, what we can do is have our chat server write those binary blobs to blob storage. And we solved half the problem here. S3 is made for multi-gigabyte payloads. It has all the guarantees that we need in terms of availability and then in terms of throughput. We should be able to store things here. But the problem remains that we are still passing a lot of data through our chat server that really doesn't map to the very small messages sent rapidly that we previously had been using the chat server for. So a simple solution for this is for us to use pre-signed URLs. You might have heard these in some of our other designs. And the idea is pretty straightforward. When our client wants to make an upload, it's going to make a request to the chat server to say, give me an upload target or an upload URL. The chat server is going to use its authentication to go and ask S3 for an pre-signed URL, which is basically a URL that has embedded authentication, usually with a TTL. So it'll say, you can upload to this URL in the next hour. The client will then make a direct request to that blob storage and then upload the media. And then it will have a URL that's addressable inside that blob storage that it can then send inside the message that it was already sending. So now instead of sending, hey, here is a message that includes the entire video, I'm going to send a message to that chat ID that includes the URL to the payload that I've already updated. Finally, when users need to receive the message, they're going to receive that URL and they're going to make a request back to that blob storage to go and grab that payload and send it onto their client. Now, there are some additional problems here. We need to be able to expire this media after it's been sent to all of its recipient. Maybe we only keep it around for 30 days. We want to manage the storage space so that users aren't unnecessarily uploading data to our S3 bucket, so they're not using us like a Google Drive. But generally speaking, this pre-signed URL regime is going to work quite well for our purposes, and it allows us to reuse the existing messaging infrastructure that we set up for our second functional requirement. All right, we're moving quickly here, and we're on to our fourth functional requirement. This is where things are going to start to get a little bit more complicated, because up until this point, we've been assuming that our transient connections to the chat server were sufficient for delivering messages. But if I want to access messages after I've been offline, then I don't have that connection to the chat server that I can use to send those messages. So we're going to need to evolve this solution a bit. So let's go ahead and give ourselves some space. First of all, I need to be able to store my messages. So I'm going to need a messages table. Let's just assume that messages have an ID, they've got some contents, maybe they have a creator ID or a sender ID, and then a timestamp. We'll assume the chat server is the one responsible for the timestamp, so we can keep it reasonably consistent. So now we've got the messages stored on our server, but how do we ensure that they actually get to the end user? Well, one way to solve this is for us to create a separate inbox table, and we'll have a recipient ID and we'll have a message ID. And the idea here is when messages need to be sent, we'll create an entry in the inbox for all of the recipients. So what would the flow look like here? Well, first of all, when we want to send a message, a client goes to the chat server and says, send message to a given chat ID, here's the contents. The chat server is going to go and look up the chat participants, so that way it knows who to send a message to. So it's going to make a query to the GSI for this table. Actually, I don't think it needs to use the GSI, it can use the primary key. Then we're going to create a transaction to write to the messages and inbox channel. So The messages table will have one record, which is the message contents and its timestamp. And then the inbox table, we will create records for every participant in that chat. Now note that DynamoDB transactions support up to 100 records. So we need to make sure that our group chats are no larger than 100 participants so we can make this transaction, I guess 99. Once we've created the recipients, now we can try to go and send messages to our clients. In the chat server, we maintain the map of the client IDs to the currently connected WebSockets. And then for each participant, where we can address them, we're going to go ahead and send the message to that client. Now, we want to keep track of delivery. We want to make sure that those messages actually got to the client. So a natural thing for us to do is when the client receives a message, it's going to send an ACK or an acknowledgement back to the chat server. So when it receives a certain message ID, the chat server is going to receive the ACK. And then at that point, the chat server can delete that entry from the inbox, so that way we don't need to send it again. Now, when clients connect to the chat server for the first time, the chat server can then unload all of the messages in the inbox that the client hasn't received. We will go and look up all of the message IDs for that recipient ID, and then for those message IDs, we'll grab their content, and we will send messages to the client, which will then ACK each of those messages and remove them from the inbox. So what we're guaranteeing here is that messages will be eventually delivered to clients. That clients, as long as they are periodically connecting to the chat server, will receive those messages. And if they are already online on the chat server, they've got a WebSocket connection, then we'll already be able to send the message over that pre-existing channel. All right, so we finally got a design that satisfies all of our functional requirements, but it does so in a degenerate way. And we're going to be reminding our interviewer throughout this process that we understand that this design doesn't scale, that we know about the problems, because we don't want them to jump to the conclusion that, hey, this guy doesn't understand, or this gal doesn't understand scaling. The next step for us is to jump into our deep dives. And this is the place where we're going to start to satisfy our non-functional requirements, deal with any questions that our interviewer might add on to the list. They might throw additional requirements, and then constantly look for places where we can refine our design. This is kind of an iterative process where we're looking for issues, resolving those issues, and then moving forward. So I'm going to go ahead and delete our framework to leave space for our non-functional requirements, which I'll drop on the screen now. Now, despite being a degenerate solution, we're actually not off to a terrible start. So first of all, this non-functional requirement of delivering with low latency is already satisfied. When clients are connecting to our chat server, they're going to send messages, we'll write those messages to the database, but since we already have all the WebSocket connections, we can deliver those messages immediately for anybody who's currently connected. So that one is satisfied. We can also guarantee delivery of messages because we're writing them on the server side to our database. So we write the messages to this messages table into the inbox. Clients are going to get those messages if they're connected, and if they're not, then when they connect again to our server, we can go and find all the messages that haven't been delivered and deliver them. Great. But the next requirement is really going to throw us for a loop. In terms of billions of users, we're probably not going to satisfy those with a single chat server, and we really wouldn't want to because of the availability problems. WhatsApp famously served 2 million users per server, 2 million connections per server, which is actually pretty high, and they're right to be proud of that. I think you could probably get those numbers even higher on modern hardware, but still, as an order of magnitude, we're gonna have to have hundreds, if not maybe 1,000 chat servers in order to support the operations that we have here. So to get to 1,000 chat servers, we're gonna have to make some changes. You rearrange this diagram a bit. So first, visually, let's include some additional chat servers. When the clients are trying to connect to our chat servers, they need to know which one to go to. The natural thing to do here is insert a load balancer, but we'll note that the load balancer here needs to be a little bit different. With a web server, our web servers are stateless. And what that means is that the load balancer
can basically terminate requests at the layer 7, at the HTTP level, and then forward those requests to an arbitrary server. So if I get an HTTP request to a layer 7 load balancer, I can forward that HTTP request to any of my stateless web servers, get the response, and return it back to my client. It doesn't need to go to a specific server. But with WebSockets, it's a connection-oriented protocol, and so I need to retain the connection between client and server, and as such, I need a different style of load balancer. This is known as a layer 4 load balancer, and the way that it works is when a client connects to the load balancer, it creates a TCP connection. It's going to go and send messages over that TCP connection. And the load balancer is going to create a symmetric connection to my chat servers. So whenever the client creates a new connection is created, and when the client disconnects, the load balancer also disconnects. And what this is going to do is effectively it's going to make this load balancer invisible to my chat servers. It's as if the client was connecting directly to a chat server. Now, the load balancer can decide which connections are made to which servers, and the most natural way to do this for this setup is to use the least connections. So when the client connects to the load balancer, it's going to choose the chat server that currently has the least open connections. The load balancer knows how many connections it's already made, and it's going to choose the one with the least. And the reason this is useful is because the chat server's primary resource, the thing that it's consuming, is that connection. Now, we can go up to 2 million connections, but probably not larger. And what this allows us to do is when we scale, we add new chat servers into the rotation. Those will be saturated quickly because the load balancer will recognize that this new server has 0 or 1 connections, whereas my other chat server has millions. I'm going to start to route inbound connections to that chat server until it's approximately equal with others. Now, setting it up like this does give us that horizontal scalability, but it doesn't actually solve our problem. In fact, it makes this first requirement break. Let's talk a little bit about what that looks like. So the client connects through the load balancer to the chat server. They want to send a message. They send a message. They are user A, and they want to send a message to user B. So normally what we do is the chat server looks up all the participants. It would find user B as the participant in whatever chat that we were talking about. It would write the message into the messages and inbox, and then it would look at its local WebSocket connections and try to pass the message back down via the WebSocket that the other user is connected through. But we have a problem here. User A might be connected to chat server 1, and user B might be connected to chat server 2. So user A isn't able to send that message to the WebSocket that user B is connected through because they're connected to completely different servers. So fundamentally, we have a routing problem here. We need our chat servers to be able to talk to one another to pass messages so that they eventually arrive at the clients that we care about. Like all good system design problems, there are a bunch of ways that we can potentially solve this. The thing that I think a lot of candidates gravitate toward is to try to use Kafka here. And the idea would be we're going to set up Kafka topics for each user. When clients connect to a chat server, we're going to subscribe to the topic for that user. And then when we want to send a message to a user, we'll write to the Kafka topic for that user. And so the idea would be if I need to send a message to a chat, I'll look up all the participants, I'll write to those Kafka topics, and then these chat servers will be reading from those topics, and they will grab the message and then send it to the associated WebSocket connection back to the client. Now, unfortunately, this isn't a very good solution, in part because Kafka really isn't architected for billions of topics. Another problem is that Kafka topics are really heavy. They're somewhere between 50 and 100 kilobytes per topic, which, when we talk about billions of users, is terabytes of data just to get the setup for both the partitions and the topics. Finally, Kafka doesn't really support this rapid connect and disconnect for many topics. It's not built for these very short-lived small topics, micro topics that we're trying to set up here. So ultimately, Kafka, probably not the best solution. A better option for us is to use a consistent hash ring. And the idea here is if we can predictably know that a specific user is always going to be owned or connected to a specific server, then whenever we need to send messages to that user, we can just send them to that server and know that it can pass them along. So how might this work? Well, first of all, we'll dump our load balancer and expose our chat servers to the web via DNS. That way, clients can connect directly to a chat server. But they may not know which chat server to connect to. So let's go introduce a chat registry. And the idea with this chat registry is it's just a way for clients to find out which chat server they need to connect to. And then finally, we're going to need some way to store our configuration. We can use Zookeeper or etcd, but any storage that we can sync between all of the nodes in our cluster so that they can be aware of where a particular user is assigned. And so the steps now to send a message, when a client first wants to connect, they're going to go to the chat registry and say, I'm user A, tell me which server, and the chat registry might say, you're connected to server 1. Now when they want to send a message to user B, they're going to write their message to server 1, which they're connected to. They're going to do the same set of processes to write their message and create it in the inbox. And now that they know that they want to send a message to user B, they're going to use the information that's in Zookeeper to find out which chat server user B might be connected to, and then make a direct connection. The chat servers are going to write to one another. So server 1 is going to write to, if B is assigned to server 2, a message that says, I've got a new message for user B. And then server 2 is going to check its internal hash map to see if user B is indeed connected to the server, and if it is, it's going to pass that message through. So we've got 2 hops instead of just going through that singular server. Now this isn't without its problems. The biggest issue with this consistent hash approach is scaling becomes a bit of an orchestration. So imagine we have 4 servers and we want to move to 5. The consistent hashing approach is going to guarantee that most of those users are going to stay on their existing host. But some of the users on the edge, about 20%, are going to get moved to a different host. The way that that typically happens is we signal into Zookeeper or into etcd that this event is happening, and then chat servers are going to slowly disconnect the users who are misassigned. If user A is connected to server 1 and it needs to move to 2, we'll disconnect them. The client will reconnect via the registry, and then they'll be connected to server 2. We need to do this slowly so that a lot of connections and disconnections aren't happening simultaneously. And while this scaling event is happening, when we want to send a message to user B, who might be on server 2 or might be on server 3, depending upon where we're at in the process, we may need to send messages to both of the servers so that we can eventually get that message to user B, which is both additional overhead and stress on our service, but also this additional orchestration that we need to run. Now, your interviewer may or may not require you to go into that detail, but it's important to understand what is actually happening during scaling events for a consistently hashed service in order to make this work. Now, while the consistent hash approach is good, it does force us to contend with this orchestration problem for scaling, and there is potential that chat servers might get hot, that the connections on one chat server might be more than on other chat servers. We basically have uneven load. So the idea behind the Kafka instance, where we had kind of externalized that inter-server communication, was good in spite of the fact that from a technical perspective, Kafka is probably not the right technology to implement this. So can we get a bit of both? Well, yes, I think we can. And the solution here that I think is a pretty good one is to use Redis PubSub. The way that Redis PubSub works is you tell Redis, I would like to listen to a particular topic, which is a string. Redis creates an internal hash map, much like our chat servers do. And then when you publish messages to that topic, Redis will look up in that hash map which sockets are listening on that topic and then pass them the message. It is a very dumb socket server in some sense. And the guarantees of Redis PubSub are pretty low. What Redis PubSub offers is at most once delivery of messages, which is to say, I might deliver it or I might not. That would normally be pretty bad, except for the fact that we do already have ways to guarantee the delivery of our messages. Remember that we're writing them to our durable storage. When clients connect, they're able to retrieve any messages that haven't been received yet. We can even have our clients periodically poll or receive some other notification that there might be messages that are waiting for them and that they need to go and get them. So we have a way to deliver those messages in a reliable way. Redis PubSub gives us a really lightweight way of having the real-time under 500 millisecond delivery of messages. So what does that look like? Well, when our users connect to a chat server, they can connect to anyone. We'll use the least connections. That chat server will register a subscription to Redis PubSub for that particular user ID. And then when we send a message and we get to that point where we want to go and notify all of the connected users that a message is waiting, the chat servers will then publish a notification to that topic, given the user ID, and Redis will pass that over to the server that's responsible for that user ID, and then that server will pass that over the WebSocket that's also associated with that particular user ID. So fundamentally, we have a way of bouncing through Redis to get to the right server and get the messages to the right client. Now, this isn't panacea. And fundamentally, we have many of the same problems that we had with the consistent hashing approach, in that if for some reason we need to scale the Redis cluster, then we have to go through the same orchestration problem of moving topics and moving connections. You have to understand for Redis, what we basically have is the topics are going to be spread amongst nodes in the cluster. And so each chat server is going to need to maintain a connection to each of the nodes of the Redis cluster. Now, fortunately, this Redis cluster isn't doing much. It really doesn't have much responsibility aside from basically echoing requests across sockets. And so we don't need a giant cluster to be able to support the throughput that we have. But we are going to require an n times m number of connections here, which if the system were to scale to trillions of accounts might become a problem for us. So now that we've satisfied billions of users, we've got one more requirement of messages not being stored unnecessarily. This gives us a bit of time. The idea for WhatsApp is that after 30 days, if you haven't received your message, you aren't going to get it. And like I mentioned in the beginning, we don't want to keep messages around that we don't need to. They end up being a privacy liability, which for Meta is incredibly important and very expensive when they get wrong. So what we can do is add a cleanup service, which is going to do this work. Our messages table, remember, has a timestamp. So if we add a secondary index on that timestamp, we can go find all the messages that are older than 30 days and we can delete them. The inbox, remember, is going to have a record for every undelivered message, and it's going to be deleted as soon as the clients receive it. If we add an additional timestamp field here, then we can use the same sort of cleanup process. When messages are received by all clients, we may also want to delete the message here. So when we are about to go and delete from the inbox, we can check to see if that is the last message in the inbox, and if so, we can remove the message. There may be some race conditions here, but remember, we've got these guardrails of 30 days, so even if we might miss a message, we're not going to miss it for long. It's going to disappear. Now, this gives us a chance to really estimate the storage requirement of the system, and if we assume we've got 1 billion users and they do 100 messages per day, then we're going to have 100 billion messages per day. If each of those messages is capped, let's just assume that the contents can be no larger than a kilobyte, then we're going to have a kilobyte per message. So we have 100 billion kilobytes, or 100 trillion bytes. And if you recall, mega is a million, giga is a billion, tera is trillion. So this is 100 terabytes. That's per day, and we'd multiply that by 30 days if we assume that all messages were going to wait indefinitely. But the reality is most messages are going to get delivered immediately and get removed by our other process. So our database is going to need on the order of a few hundred terabytes. This is a lot of data, but not an unheard of amount, and certainly achievable by modern systems. Our interviewer might ask us a few extensions to this problem. So one extension would be to allow users to have multiple devices. How does our design need to change? Now, all of our tables currently are keyed off the idea that the recipient is a user ID, that basically a user would get one message. There's kind of a one-to-one relationship. But if they might have multiple devices, then we're going to need to add a new notion. And what we can do is add a client with a user ID and then maybe a client ID. Now we need to go and update our design such that everything we are referring to a user, we need to refer to the client. So our inbox, for instance, would have a recipient client ID. And our pub subtopics would now be clients. Now, when a client wants to send a message, they're going to look up all of the participants. And then for each participant, we're going to look up all of their clients and then send messages to each of them. Now, this would greatly increase the number of rows that you would need to insert into the inbox table in the instance where, for instance, you've got 100 people and they've got 5 devices each. So we would probably want to put some limits on the number of active clients that a user could have. Maybe they can have 2 or 3 devices. And then we would need to go and percolate that restriction through to the group size to make sure that we're not running afoul of that DynamoDB transaction limit where we can only insert 100 records at a time. A final extension that you might get asked is about presence indicators, or whether someone is available. And the idea for this is you open up your app and you see your contact list, and you'd like to see little green orbs next to those people who are online, and then maybe no orb or a red orb for those people who aren't. This requires some product design. We really need to specify the requirements of the feature, because we need to know which users care about the presence of other users. You could do this in a very simple polling fashion by keeping a table which has whether a user is connected or not, and then querying that table whenever you want to see whether that user is currently active. And so what this would look like is when a connection is established to the chat server, it would write to a new table. Maybe this is available, user ID, and status. And then when a connection happened, it would write a status of available. And then when you disconnected, when the WebSocket connection was terminated, then that status would be set to unavailable. Now, in a lot of cases, people want to get notifications about when that's happening. If you had the screen open, you'd want to see things that are changing. And we would probably use the existing PubSub infrastructure for this. So we would need some way for users to indicate their interest in the availability of a particular user. They would have to subscribe to that somehow. And then whenever those disconnect events happened, we would publish to that topic and then pass those events down to the clients that are concerned with it. A big challenge here is deciding which users I care about watching, because there's obviously some immense fan out that could happen here. What we probably don't want is when a user to get disconnected for us to have to send out thousands or tens of thousands of notifications. So we need to figure out how we can constrain the number of users who can be watching a particular user at a certain time. But those would be the types of things that you might go into with additional time in this interview. Okay, so we touched on a lot of information in this problem. You might be asking yourself, all right, how much of this do I actually need to know for an interview? And this, of course, is going to vary depending upon how grumpy your interviewer is and the companies that you're interviewing for. But generally speaking, for mid-level candidates, the expectation is that you're relatively new to system design. And so where we touch on things like WebSocket management, consistent hashing, and pub/sub, database design, the expectation is that you're not going to be particularly deep in any of these areas. Now, you should be roughly familiar, and being able to call out various challenges that you're going to run into is definitely a bonus, but the interviewer is not expecting you to come up with a perfect design out of the gate. For more senior candidates, they are expecting you are going to be familiar with all of these core concepts, that you have an idea about how load balancers work and how WebSockets work, and you have an idea about how consistent hashing might enable scaling of stateful services. You are going to make mistakes. Everybody does. Your interviewer isn't expecting any specialist knowledge, but they're going to expect that you do a pretty good job in putting together a system that scales and satisfies the requirements. For a staff level candidate, you're going to really zoom in on the interesting parts of this problem. So your interviewer wants to see that you really understand that the statefulness of these chat servers is pretty interesting, and that the data model is in service of really rapid querying and then also very fast writes to be able to support the throughput that we're talking about. And so what they want to see from you is that you're able to zoom in on the hard or important parts of the problem and then generalize your knowledge and your experience to be able to come up with solutions that are going to work for a particular instance. It's not the case that staff level candidates are like senior candidates, but just even better. They're going to focus on qualitatively different pieces, but they're also going to be able to bring in a much larger toolkit of approaches and experience that their interviewer is going to be able to see. Managers, generally speaking, are usually held to about a senior level of standard across most companies. There are some exceptions to this where managers are held to a staff level standard, but they are very much the exception rather than the rule. That's usually not the case. Anyway, I hope that this breakdown was useful for you. We have the write-up available on our website, so if you've got questions, feel free to comment below or comment on our guide, which walks into some of these things in greater detail. And then highly encourage, if you've got questions around SSE or WebSockets or about consistent hashing, to read up on our real-time updates deep dive, which goes into a lot more detail and spells out some of these concepts so that you're able to use them in an interview. Thanks for spending time with us. Love your likes and subscription if you found value here. And otherwise, until next time, I'll talk to you later.